Alright, this is Unit 5, 5.1, Theorems of Polynomials. So before we get into it too much, I want you to think, what does the word root mean in math? And write down an answer right there. So pause this, write down an answer what you think root means. Okay, so other words for root: zeros, solutions. Okay, x-intercepts. So remember when you were graphing polynomials last year, the roots were the x-intercepts. And when y became 0, that was what x was. So if you remember, that was the x value when y becomes 0. So think of root, memorize that if you didn't already have it memorized. Important word to know. So we are going to spend our time looking for 2 days. So this is going to cover the first half of the week and the second half of the week. We're going to cover these theorems: the fundamental theorem of algebra, the zero product property, rational root theorem, remainder theorem. So read our objective right there, please. Okay, so the degree of a polynomial equation tells you how many roots the equation has. So kind of going back in time in your math history, if you had 3x plus 5 equals 11, so the exponent right here was 1, right? And so you minus 5, you got 3x equals 6, you divide by 3, you got x equals 2, okay? Compare that to when you did x squared plus 9x plus 20 equals 0 last year, and you couldn't solve like we did earlier. What you needed to do, if you remember, was factor. And then you had x plus 5 equals 0, x plus 4 equals 0. You minus 5, minus 5, minus 4, minus 4. You got x equals negative 5, x equals negative 4. So I want you to notice a pattern here, please. Okay, so let's go back. The degree of a polynomial equation tells you how many roots. What's a root? Yeah, zeros, solutions, or x-intercepts. So notice the degree of the first polynomial that we did was 1, and we had 1 solution. The degree of the other polynomial, the quadratic that I wrote, was 2, and it had 2 solutions. Okay, it's easy to see graphically that every polynomial of degree 1 has a single 0, the x-intercept, right? So remember, linear. However, looking at this, it gets a little bit intense, right? So obviously we have 2 solutions there, 2 roots. Here it looks like we only have 1, and there it looks like we have none. But if you read underneath, you'll kind of get an idea. So what I want you to do again is pause this and solve these. Alright, so we're going to solve this first one by factoring. So if you remember, we get 0 equals x squared minus 4. So we've got to think of something that multiplies to give us negative 4, but adds to give us 0, right? That'll be x minus 2, x plus 2 when we factor that. So x minus 2 equals 0, x plus 2 equals 0, and we solve, and we get x equals 2, negative 2, negative 2, x equals negative 2, boom, 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 right? And we have those 2 zeros at negative 2 and 2, the 2 solutions. The degree was 2. Okay, now we're going to factor this guy. We got to think of something that multiplies to give us 1, but adds to give us negative 2. Seems like that's going to be negative 1 and negative 1, right? So when we set those equal to 0, if you remember last year doing this, that's good. If you're not remembering it, maybe pause this and come email me or ask for questions. Alright, so we do have 2 solutions too, but they are the same. And you're going to notice here we have multiplicity of 2. So the same thing happening twice. Okay, and over here we're going to use the quadratic formula. And remember, x is equal to negative b. What are we doing? Remember, we're solving, right? And we know that the degree is 2, so we're expecting to get 2 solutions. X is equal to negative b plus or minus a square root of b squared minus 4ac all over 2a. My a was 1, my b was 2, my c was 2. So hopefully you already did this, and this is just making sure you did good. So you have negative 2 plus or minus the square root of 2 squared minus 4 times a times c all over 2 times a. The solution is going to be the answer here. So we have negative 2 plus or minus, that's going to be 4. 4 times 1 is 4, 4 times 2 is 8, 4 minus 8, which is the square root of negative 4, all over 2, which is going to give us negative 2 plus or minus 2i divided by 2. 2 divided by 2 is negative 1. 2i divided by 2 is 1i. So we have two roots, negative 1 plus I and negative 1 minus I. But they're both imaginary, right? So we couldn't see them. They weren't real roots. But they're still there. So it still had two solutions even though we couldn't see it. All right, continuing on. So every quadratic polynomial equation has quadratic's degree 2. Okay, so we'll have two roots. Every cubic, x cubed, will have, yep, you got it, 3 roots, and so on. This is called the fundamental theorem of algebra. So read through that with me. If p of x represents a polynomial of degree, any degree, right? As long as it's not negative or 0, any degree, x to the 5th, x to the 4th, right, x squared, then when this equation equals 0, it's going to have n roots. So the same degree will be the same amount of solutions or roots, including the multiples and complex. So I want you to put that in your own words right there, please. Just sum it up. Really do that. Okay. All right, so how many roots does each of the following equations have? We're going to first find the degree. Remember, the degree is the largest exponent. So this will have 4 solutions, 4 roots. Okay, over here, the degree is 15, right? 15 is bigger than 6. So that's the degree is 15. There will be 15 roots. I don't want to solve that. Hopefully you don't want either. All right, so one more time, I want you to write in words, in your own words, explain what a root is. Please do that. Pause this and do it. Okay, next theorem. Do you understand this one? Right, so whatever the degree is, that's how many roots, how many solutions it could potentially have. Don't forget, some of them could be complex, some of them could be multiples. So you might not visually see them all, but they do all exist. Okay, so the zero product property. Okay, read through this. Any value of x that makes one factor of a polynomial equal 0 will make the whole polynomial equal 0. So just kind of think, if I had 3 times x, we don't know what x is, but it could be any number, right? And then we find out that it equals 0. 3 times what can create 0? There's no other options, right? Sometimes with other numbers, like if we had 3, like there could be other options there sometimes, depending on the equation. I don't know what I'm talking about. Sorry, let me start over. 3 times whatever equals 0. We know that that has to be 0. Okay? There's no other options. All right, so any value of x that makes one factor of a polynomial equal 0 make the whole polynomial equal 0. Okay, so looking at polynomials, right? This is kind of what you did last year. If you have x minus 1 times x minus 2 equals 0, yep, this whole thing could be 0. This whole thing could be 0, right? To create 0, one or both of them have to be 0. Okay, let's read through that. Just a quick reminder there. Lots of reading today. So the following polynomial equations are written in factored form. Find all solutions. Okay, because they're multiplying and equals 0, one or all of them could be 0. Remember the zero product property. Okay, so we set one or all of them equal to 0. Okay, so we're going to add 4. What we do to one side, we have to do to the other. We're going to subtract 8. What we do to one side, we have to do to the other. we are going to add 2. What we do to one side, we do to the other. Now look real quick. If I take this 4 and I put it in for x, it's not going to give me 0 in every single one, right? So 4 minus 2, 4 plus 8, 4 minus 4. That's going to give me 0 times 4 plus 8 is 12, times 4 minus 2 is 2. 0 times anything is 0, right? So it doesn't matter what these guys become, but because that one created 0, the whole answer will end up being 0, okay? And you could prove it with all of those. If we plug in a negative 8 here, I'm not going to get 0 here, but I will here. And because there's 0 in that multiplication, it will create 0 in the end. So the 0 product property tells us all the ways we can create 0 there, and there are 3 ways. So here you do this one, x equals 0, x plus 6 equals 0, applying the 0 product property equals 0, minus 6, x equals negative 6, plus 5, x equals 5. So all 3 of these numbers will make this 0. Differently, but they will all make it 0. Okay? Okay, also, it may be useful to determine whether or not a given number is a 0 of a polynomial equation, right? So we want to know, is it a solution? To help us do this, we have the remainder theorem. So the remainder theorem is going off of that synthetic division that we did last unit. So if you remember synthetic division, a lot of times we divide. I'm just going to, not really write numbers, but I'm going to remind you. You had your opposite number right here. Let's say it's negative 1. Then you had numbers there. Okay, and you brought down this number. These are not the actual numbers. We multiplied, and then we put it here. We combined it. We got something here, right? And if we got 0 as our remainder, that meant it was a factor. Okay, so instead of making you do synthetic division every single time, the remainder theorem was discovered, and it's awesome. It saves us some time so that we don't have to do synthetic division every time to see if it is a factor. Which will then determine that it could be a solution. Okay, so if you have a binomial, like we did with synthetic division, we always flip the sign. So notice the sign does flip, okay? And that goes back to solving for x also. So if you take the opposite sign of what you're given in binomial, and we plug it in for every x, then that will be what the remainder should have been. Okay? All right, so this a, remember it flipped signs, so it was x minus 3. So I'm just going to quickly show you synthetic division. So we flip it, right? And then we're going to pull down 6, negative 1, 4, 3, right? We pull down the coefficients. Then we bring that down and we multiply. 6 times 3 is 18. That's going to give us 17, right? Woo, 3 times 17. Been a while since I've done that big. I could have probably done it in my head, but I'm trying to save time. Okay, and then combine those. I get 55. Wowzers, right? And then 55 times 3 gives me 165, which is going to give me 168. That is a big remainder, but that's our remainder. Okay? Now I'm going to do the remainder theorem. So the remainder theorem says that you take the solution to that binomial, right? So the opposite sign right there, and I'm going to plug it in to the polynomial. It's going to replace all the x's. Now, when you plug this into your calculator, be careful, because what you plug into your calculator, if you plug it in wrong, obviously it's going to give you the wrong answer. But I just need you to be very careful as you're plugging this in, please. So go ahead and do it. And notice you get 168. Whoa, right? Really cool. So why is this theorem important? Well, now we know that 3x minus 3 is not a factor, and we didn't have to do synthetic division. We could have just put it into our calculator. Okay? All right, so it's really awesome, really cool. So let's do this one real quick. Put it in your calculator. We're going to put in 0.5 because that'll be faster to type into your calculator. So I didn't have to do synthetic division on that one before. I was just showing you what the remainder was and then how cool the remainder theorem is. That, doing synthetic division, obviously we're going to find the remainder. Oops, I put the wrong exponent real quick in my calculator. Alright. And we get 10. So the remainder was 10. So is x minus 1/2 a factor? No. Why am I writing x? Sorry, it's 10. Not a factor. Alright, the reason that this is important is that we can use the remainder theorem to see if p of a equals 0. If it does, then a is a 0, the polynomial, and one of the solutions that we're looking for. Okay, so we're going to pause right here. We are spending 2 days on this, so we'll pause, and then you're going to come back on Thursday or Friday and find out the rest of the story. So there's going to be a short assignment posted, and follow the instructions and do those, please.